Okay, extremely sorry about the delayed start today. Um, so this is what we had in our last class, that we had a test like this, a very simple one at that. We did it with Blender. In today's class, we are going to look into what happens underneath. If you're going to build something over here in Blender and you want to export it to any other 3D software, or you want to write a program in C++, Java, or Python, you want to load this particular model into that. There has to be a common format for this. Because if you look at this blend file, see when I save it or go into save as, the extension that we are saving with, it's a blend format. What happens in there, if you try to read that file, let me show you right away. I think it's my desktop, right. So we got this desktop blend file over here, and if I want to see the content of it, we can do that in Linux terminals. You just type in cat for concatenate and you type in the file name. So that's going to be desktop blend. So this is what we have. That tells you that this is a binary file. It's not really human readable. You have to know the file format, the specifications of it, exactly which byte contains what. And that's not really difficult for Blender, because this is open source. The blend file format, that's also open source. It's just that the other 3D applications, they need to know, they need to understand this blend format. Okay. That's why, I mean, this is not really a good format to use for other 3D tools. What we're going to do instead is we will go for something called a OBJ file. Now, let me start with something very simple, because this has a lot of separate objects. I want to start with something very simple. So I'll go for new. And before I forget, let us bring in the screencast. Okay, so right now we got a cube. It's a very simple object right there. And we can write this to a text file. If you just say file export and then wavefront.obj, let me zoom it up for those of you who are at the back. Okay, so from the file menu, if you go into export and then you have wavefront.obj, when we hit that, we get a choice like this, and let me save it to my, say, desktop, and this is going to be a cube. The file format, let's zoom up again. Right, so the top text field shows you the location, and then you can see that the file format is cube.obj. It's an obj file format. And down here, we got some options over here. Okay. So when you install Blender by default, what you'd have at home is that these two options, write normals and include UVs, they will be checked off by default. In last semester, I made some changes to this default setup because we were using for a different purpose. So I had this write normals checked and include UVs checked. By default, they will be checked off. Okay. So if you have them checked, it will spit out. It will write some extra information. If you don't have it checked, you won't have that information over here. So this is a simplified version. By default, that's the setup you get. Now, when we wrote that, we wrote it to a cube.obj file. Let me try the same thing again. Let me look for the obj files over here, and as you can see, oh, sorry. Right, so we are here on the terminal, and we see that there is a cube.obj file, this one, and we can try looking at the content of it. See, this one's a plain text file. So this is very much human readable, and most 3D software, they would know this format. Not just 3D tools, if you look for solutions on the web, you can upload your models in .obj format and they can be rendered. So in our first lecture, I introduced some sites like BlendSwap or Thingiverse. You can actually upload your OBJ files over there and they will get rendered. Okay. So this is a very common format for people to use. Yeah, I think I need to move it out a bit. All right. That's better. So if you look at this file format, we need to understand what each of these lines are saying. Okay. On the very first line, you see that there is a pound symbol. It says Blender version 2.78, and then there is the Sub-Zero OBJ file, and after that we have another pound symbol. It says www.blender.org. Okay. These lines, they all start with a hash sign, and for this OBJ file format, any line that starts with a hash sign is treated as a comment line. Okay, so you can ignore that. I mean, you can write which tool was used to create this file and other related information right there, who created this file, who designed this model. Those sort of things can be put in comments, but otherwise you can ignore them. And in the next line, we see there is another line that says mtl lib cube.mtl. It talks about another file that can be used as a material. Okay. Whenever you're describing a 3D model, it needs to be rendered out. And I would be using this term quite a lot, rendering. What it really means is that you're going to produce a final result, the result in terms of a still image or a movie. That's rendering, okay? So when you render something out, it will really matter depending on the type of the object. So let's say my skin is of a different material compared to this leather wallet or this key ring, right? This is steel and this is skin. Well, and this is also skin, but of a different type. Okay, and we don't really need to touch them, right? Our eyes are trained. Like when you look at this thing, you don't have to know that this is steel. It already gives the vibe of steel because it shines in a particular way. It has a distinct color, and we know that it is of this type. So all the materials that we see in our real life, they have a very particular property in many different ways that tells us what type of material it is. And when we try to render something out, that needs to be described in similar fashion. What are the different materials that this thing is created with? Now, since we're starting this off, I'm not going to talk about material properties right away. We'll be covering that later on. But what I want to tell you is that those material properties are written into a separate file, and that file name is cube.mtl. This is necessary but not needed at this point. Let us just assume that someone will write that file. And right after that, we got a line that says O cube, which means that we are going to describe an object, and the name of the object is cube. Okay, we can change the name. I mean, we can do that in Blender quite easily. And after that, we got 8 lines. You can count them. There are 8 different lines, and all these lines, they start with V. And V stands for vertex. We are describing vertex. Since we are describing a 3D model, this is in the 3D. Each of these vertices, they will have 3 coordinates: X, Y, and Z. Okay, so we'll have that segment right here. And before I go any further, let me just show you what we have in here. So if you look at this model, this is a cube. A cube really has 8 corner points. Okay, we can see all of them right now because some faces are hidden. they are behind, but you can see 1, 2, 3, 4, 5, 6, 7. Excuse me. Where's the eighth one? It's somewhere over here. And Blender has a nice shortcut key to view what's hidden. We say that this is wireframe. If you make this transparent, you can see that. Okay. Z for toggling from solid, and this is called the wireframe. So let me write this down. We have a solid view, and we also have a wire view or wireframe view. The one that you're looking at is called the wireframe view because these are like wires right here, and it captures the frame. So in the wireframe view, you can actually see this this vertex over here. So all these things, we treat them as vertices. Right? These are all vertices, the corner points. Okay. Now for each of these corner points, we will have coordinates. We'll have x, y, and z values. In our previous class, I said that in Blender, we got these arrows, and they point to 3 major axes. The color code, red, green, and blue, they're aligned with x, y, and z. Okay? So when you see that there is this red line, this is the x-axis, this is the y-axis, similarly like for the green one. So can we tell the coordinate of a particular vertex just by looking at this x, y, z values? And if you know the origin, can you calculate that? See, right in the middle, let me show you in this format, and let us clear out all these things that I've written. By the way, there is another very handy shortcut with 5, number pad 5. This is the orthogonal view, and here's the perspective view. I'm going away in a different direction, but let me just introduce this thing. See, in real life, the further an object is from our eye, the smaller it becomes. We know that, right? If you're standing in front of a rail line, if it goes away in a distance from your eyes, you'll see that it's trying to come closer together. It's still parallel, but you don't see it in that way. So if you look at these two lines, they're parallel lines, but as they go away from your eye, they're meeting together, they're coming closer together as you go up. Okay. So this is how we see in real life. We see things in perspective. Okay? But often when we're designing something, we have done so in our physics course or in some other courses. When we draw objects, we sometimes keep parallel lines parallel because that helps us measure things properly. So the shortcut to use over here is number pad 5. It switches from perspective view to orthogonal view. So in orthogonal view, what we have is all these parallel lines, they stay parallel. Okay. This allows you to measure things better. So for example, if I'm looking from the top, it's not exactly top. You can go to the view menu and click on top to look at the object right from the top view. Okay. If you're looking for the shortcut, 7 is for top, 1 is for front, 3 is for right. Right, front, and top. 1, 3, 7. You'll have them memorized without memorizing them, but I mean for now, you can just go to the view menu and look at that. Since this is a cube, all the lengths will be the same, right? A cube has the same length for all the sides. Now if you're looking at the top view, what does it tell you? What is the length of this cube? For each of these sides, what is the length? See in Blender, this is actually a little bit harder to see probably from the back. If you're using Blender on your computer, you'll probably see it better. There are grid lines drawn. Okay? And all these major blocks that we have, they're 1 unit long. So 1 unit over here and another unit over here. That makes the length of each side 2 units. I'll go for a different color palette, then the grid lines will be more obvious. But right now I don't want to switch that. So what I'm saying is that this is 2 units long. Okay, and the same thing goes for all of the sides. Okay, and this one over here, this is the origin, which is 0, 0, 0. This is in 3D, 0, 0, 0. Is this clear? All right, so help me out. Let me switch to perspective view because that's easier to see sometimes. Can you guys tell me what is the x, y, and z coordinate value for this particular vertex? Let us call this vertex 1. 1, 1, 1. Z is minus 1. And x and y, you're saying that that's 1 and 1.
Y minus 1.
Alright, so 1 minus 1, and then
X 1, and Y minus 1, Z minus 1.
do we all agree to that? No? Yeah, that's what I'm asking. Okay, let's try to understand what's happening, okay? We have this green line that's separating the entire thing into 2 halves, right? So over here, if you follow this line, this is x positive. And if you go to the left, we have x negative, right? So since this point is on the right side, and we have this whole thing as 2 units, so this must be 1 unit long. That tells you that x is equal to 1. Is this part clear? Let me know. I mean, if you don't understand something, let me know right away. Okay. So over here we got x equal to 1. And let us look at the other thing. This origin is right at the center. If we split this cube into 2 halves, like this, okay, if you go away in this direction, that tells you y is positive. If you come forward like this, then y is negative. So in that case, which direction are we going? Further away or towards our case? Towards us, right? So over here, y is in the negative direction. And this thing, the whole distance over here, that's 2 units. That's 1 unit then. Half of it is 1. So 1 in the negative direction. That's how y is minus 1. And finally, if you're going to find out z, you'd see that the total height is divided into 2 parts. This is 2 units long. So this is 1 unit over here and 1 unit down here. Are we going to the top or are we coming down over here? We're coming down, right? So that's negative. That's negative z. And that's why z is again minus 1. So altogether we got 1, minus 1, and minus 1. And what Ibrahim said was right, that this is the coordinate for this point, V1. So let us try one more. Can you tell me what do we have over here? X minus 1. X minus 1, yes, that's right. So because we're going to the left. Yeah, y is positive because we're going farther away, and this is on the top surface. Z is also plus 1. So we can actually find out the coordinates just by looking at these things if we know the measurement. And interestingly enough, what's going to happen is that you can actually test whether you're telling the right thing or not. If you bring out this properties tab and also switch to something called the edit mode, by default you'd be at the object mode. And let me zoom it up over here. there are some other options like edit mode, sculpt mode. I'm not going to talk about these things. We are for sure going to use them, but not right now. Right now, we'd only be working with two modes, the object mode and the edit mode. And we'll be switching through them quite a bit. So you need to know the shortcut for that. Tab to go into the edit mode, tab, and tab again to come out in the object mode. What the edit mode allows you to do, it allows you to edit the geometry of it. You can change the shape. You can play with the points. You can move them in any direction. You can play with the edges. You can do all that. So right now we're in the object mode, and if I switch to the edit mode now, I can select individual vertices. Like I can click over here, and if I bring up this properties tab with the N key, if you go to the top right of the properties, let me zoom up again. So it talks about the vertex. So that was our vertex 1, and we have 1, -1, and -1. So yeah, it validates our claim that you can click on any such vertex. So for example, if I click over here, you'll see that the coordinate, they change. It becomes 1, 1, 1 because I clicked on a different vertex. If I click over here, see that changes again, 1, -1, and 1. Is this thing clear? Okay, so let me come out of this zooming thing. So for each of these vertices, we can somehow find out the exact coordinates, right? Now, if you look at the OBJ file, see, this is exactly what's being written. There were 8 different vertices, and all their coordinates are written out in this fashion. The first column is for x, the next one for y, and then we have the z. So we got these 3 things, the x, y, and z values for our 8 different vertices. Okay. But the vertices alone, they're not going to describe the object. Okay. Because if you're just looking at the vertices, they can be joined in many different ways. And if you just ignore all these lines, and if you ignore all these polygons, these quadrilaterals we got, if you just consider the vertices, we'll have a point cloud. There will be some random points, and nothing will be connected. You need to tell how these points are connected together to form each of these faces. Let me take this tissue paper box. It served me well with the other section. Say this is our cube. Like, I mean, this is not a cube, obviously. It's a box. These are the corner points, right? And if I'm going to render just the points themselves, I won't have this thing. This surface won't be there. Because no one's going to tell me there's this point is connected to this, and then we connect that to that point, and this way. So if you just get the points, that's not going to be enough. That's the thing I want you to understand. What we want to tell, though, is that we have a polygon with these 4 points. And again, another polygon with these 4 points. So each of these polygons will make up this 3D face, this 3D object rather. This is what we call a polygon mesh. Anything that we see in our 3D world, these are all fake things. This is real, but that's not, right? That's a model that we are making. It may look like a 3D object, it may look realistic, but that's not real. What any of these objects are made out of are a lot of polygons. Okay? So these polygons, we call them faces. These are vertices or points, and these things, these are faces. Each of these polygons, they're faces. So let me ask you, what's the minimum number of vertices that we need to make a face? 3. 2? 3. All right. So let me show you an example. If you have 2, you can only make a line segment. You cannot enclose any area. So that's not enough, right? You need a little bit more than that. With 3 vertices, yes, you can make a triangle like this, and that can be a face. Okay, so 3 is the minimum number. And excuse me. Let me switch to another tab and add a new object. So if you go into the Create tab, there are all these options. You can also press Shift A to bring out the shortcut to add a new object over here. See, we got UV spheres. This is a sphere, but this is not really a ball. It's not one solid thing. It's actually made out of a lot of polygons. This is a polygon. This is a quadrilateral. We have another quadrilateral right here. And if you join all these quadrilateral together, they form a sphere. Is this thing clear? Okay, spheres can be drawn in other formats as well. There's another variant that says icosphere. This is a little bit different. The regular sphere that we had was made out of all quadrilaterals, polygons with 4 vertices. But over here in this icosphere, we have all polygons with 3 vertices. So let us try something else. Let us go for a cylinder. All right, looks like a cylinder, right? And you can readily see that we have a lot of rectangles or quadrilaterals that are making up this side. Okay, so all these polygons, they have 4 vertices, 1, 2, 3, and 4. So all these side faces that we got, these are quadrilaterals. However, if you look at the top face, what do we have in the top face? A circle? Actually, we don't have a circle. It may look like a circle, but what we really have, let me lower the number of vertices. Let us bring it down to 16. We had 32 vertices. That's what made it really smooth. Now we have 16 vertices. Now it doesn't really look like a circle. We got the edges coming out. If I drop it down to 8 or 6, well, it became 16. So 8 vertices over here, 6 vertices over here. If I keep on lowering the number of vertices, do you see it as a circle? Okay. So what we see as a circle is nothing but an illusion. It's just that we had many more vertices to cover. So over here, the top face is nothing but a polygon. Okay? And that's what everything boils down to in 3D graphics when we're talking about all these 3D meshes that we're building, the models we're building. They're nothing but polygons. There are a lot of polygons joined together. Okay? So far we were talking about the vertices, but as we saw that the vertices are not enough, you need to have something else. You need to say how they're connected together to form a face. Okay? And that's what we have over here in the bottom segment. You see we got 6 different lines that start with F lines. Okay, F character. F is for face. Okay. So this particular line, F 1, 2, 3, 4, what does it mean? It means that it's talking about a face, and to form this face, you're going to use 4 vertices. Which 4 vertices? Vertex 1, vertex 2, vertex 3, and vertex 4. Which one's vertex 1? First one. So all these lines, they're all V's, right? But this is vertex 1, this is vertex 2, this is vertex 3, and so on. Okay. So if I'm to copy this part, let me take this because I can't write over here. And let me open Journal or any other editor. Um, let me paste this thing over here. What I'm saying is this first line, this is vertex 1. This line is for vertex 2, and so on. The last one is, yeah, vertex 8. So we have 8 different faces, and they're saying how each of these vertices are connected together to form a face. So these lines, they may have 4 numbers when we're talking about quadrilaterals. When we are talking about triangles, they will have 3 numbers. They will give 3 vertex numbers that will be connected together to form a triangle. If we have a pentagon, then we'd have 5 points. Okay. If we have a decagon, then we'll have 10 different numbers over here that will form a face. Is this thing clear?
Sir, I have a question.
Yeah.
Sir, if I connect three vertex,
Yes.
that is called polygon or?
It's called a polygon. It's also a triangle. I mean, for specific things, like if it has 4 vertices, we call it a quadrilateral. If it has 5 vertices, we call it a pentagon. 6, we call it a hexagon. Then heptagon and octagon. It goes on. So, I mean, those things, they have specific names because they have fewer vertices. But if you're talking about 100 vertices, that's a 100 gon. I mean, definitely has a Latin name. I don't know about. So yeah. So the next important question is, why do we have 6 lines? Yes, we have 6 faces. So if you try to imagine this to be a cube, we have 1, 2, 3, 4, 5, and 6 faces right here. That's why we are talking about 6 different faces right here. Okay. And interestingly, things will change automatically. Let me try this out. Say, let me delete this and let us go back to this cube. Okay. Like I said, if you go into the edit mode, it lets you change the geometry of the object. So I can select each of these edges and I can drag them along like this to change the geometry. I can also select 2 vertices like that to select an edge and change that. Or I could also select a face and drag it along together to change it somehow. We can also apply all these things like scale for S, and then you make it smaller. And I haven't showed you rotate, but R is for rotate. Okay. So you can pretty much modify the geometry as you want right over here. Then the point that I want to make is that, let's say you change things around and you save that, like you export that to wavefront OBJ. Let me rewrite that into the cube file. See, when we go into our terminal and look at this cube object again, see, some of these vertices have changed their coordinates because we have edited the geometry. So whatever change you make over here in the 3D model, they will be reflected in the OBJ file accordingly. Is this thing clear? All right. Let us switch back to this then. So all these numbers, we're talking about these vertices, and one crucial thing to understand is that why would you write it in 2 separate segments? We declare the vertex segment separately and then the face segment. Why do we do this? I mean, why not write it in this fashion? Since we're talking about the faces, let's say the first face, we have vertex 1, 2, 3, 4, right? So why not write it in this format? 1.0, 1.0, 1.0, let's say that's the vertex, the first vertex. Or actually, let me copy it from here. 1 minus 1 minus 1, that's the first vertex, right? And the second vertex we have is 1 minus 1 and 1. 1, minus 1, and 1. And then we have minus 1, and 1. And finally, what do we have? Minus 1, and minus 1.
So কেসের মধ্যে তো একই সংখ্যা অনেকবার রিপিট হচ্ছে ওইটার রিপিট যদি হচ্ছে
In this phase,
না এই কেস যেগুলো লেখা আছে
yeah, in different phases, things will be repeated. I mean, this may look like a simpler notation that we have everything available. When we are talking about a phase, we have all these vertices available. But it has a lot of repetition in terms of common vertices. So if you look at this real life example, in this box, if you look at this vertex, the same vertex is shared in this face, on this one, and over here. So 1, 2, 3, 3 different faces, they're sharing the same vertex. If you're talking about a vertex means 3 different numbers. So these files can be written in a more compact format if you separate out the vertices and then the faces. Okay. All right. So this is kind of obvious, but I still wanted you to understand that there is a reason for us to do it in this fashion. And once you have it in this way, you can create data structures. You can create a vertex class, make all these vertices and put them together in an array or a list. And then you can have a face structure or a face class where you describe all these faces, like all these index that you have for the vertex numbers. You can put them in an array or a list or whatever data structure you feel like. Okay, but the order is important. I mean, it is not the same to say if I name the vertices 1, 2, 3, 4, and if I say 1, 3, 2, 4, they don't mean the same thing. Okay, the order is very important. And let me show you right away over here. Let us just try to assume that this is 1, this is 2, this is 3, and this is 4. Well, this way. Let me write this down. 1, 2, 3, and 4. Okay. So we can form a quadrilateral like this if we go through these vertices like this fashion, right? 1, 2, 3, 4. But for some reason, if I write 1, 2, 4, 3, then we don't have that polygon anymore. We get a hourglass-like pattern like this, a crisscross thing. So that's bad. And this one, 1, 4, 3, 2, that's not the same. 1, 2, 3, 4, and 1, 4, 3, 2, though they describe the same rectangle, they're not the same. Okay. That's again another important distinction you need to understand, and that comes from the counterclockwise and clockwise rotation. Okay. We're following two different patterns. This is counterclockwise, going against the way your clock hands move. This is counterclockwise. We're going to follow this because this is related to something we have studied in physics. I hate that. The right-hand rule. Okay. For vector cross products, it's related to that. I will explain to you why that's needed. Okay. And those of you who are here in the first class, I insisted that you really need a good knowledge of vectors to be in this section. Okay. All the math concepts, well, not all, but most of them, they will be based on vectors. And in today's class, we'll be talking about some of those. So is this thing clear? What we have studied so far? Okay. So if you're given any sort of shape, let me start with a very basic one again. We can start with the cube, but before going that, let me show you a cool little thing. We have a monkey head by default given to us in Blender. You can invoke that, and that also shows you that at the end of the day, everything is a polygon mesh. This monkey head um, is not a cube. It looks like a monkey head. Well, it will look more like a monkey head if I make it a bit more realistic. Um, I'll explain what I'm doing later on, but let me do that anyway. See, now that looks much more realistic, right? But underneath everything, what you have is nothing but polygons. That's the point I want to make. Okay. So in order to render this out, like right now it looks pretty good. I mean, we don't have the lights properly set up, but we could do so. If you bring the lamp from here to down here somewhere and then render this, this will look better. It's just that we need to understand how everything is rendered out. We need to understand the concept of reflection, shading, and how each of these pictures are produced. So what you see over here in this picture, this is the final result. Okay. For each pixel, we know about pixels, right? Whenever you look at any picture, if you zoom it up enough, you'll see that there are nothing but boxes with different colors. These are called picture elements, smallest element, and that's what we call pixel in our terminology. So when you look at the pixel level, we need to tell exactly what color we need to put in over here to make up this object. Okay. What do we have? Let's say we don't have Blender, but with some software, it could be 3D Studio Max or Maya or whatever software, you have a OBJ file. What does an OBJ file give you? It gives you a description of an object. Tells you all the vertices, tells you about all the faces you got, but finally you need to render that out on a picture like this. That's the render result. So our task, if you're going to write a software like that, that reads in a OBJ file and produces a picture for you, you need to be able to put colors to each and every pixel, because that's what the final result is, right? So somehow we need to learn that if I give you the vertices, if I give you the faces, and maybe somehow I describe the material, you can produce the final result. That's what we'd be learning. And for that, we are going to revisit something that we learned in physics. Okay, I'll try to keep it simple. This is something we covered in optics. Let's say we got a flat surface, okay, and we have a light source, like a bulb of some sort. It's emanating light rays like this. Light rays are coming out of this light source in many different directions. What's going to happen? The light rays are going to come from here and fall on this surface, and it's going to bounce off or reflect. Okay, so let's say we have an eye that's looking at that reflection. Okay, so what's going to happen? That this light ray will bounce off over here. But they do bounce off following a rule that the incidence angle is going to be equal to the reflection angle. Okay. What is the incidence angle? The incidence angle will be created with the surface normal. And the reflection angle, it's not going to be like this, it's not going to be like this, but it's going to be something quite equal. I can't really measure that, but let us just assume that that's equal. So what I'm saying is that over here, this angle, the incidence angle I, is going to be the equal to reflection angle R. Okay, we studied that as, I think, law of reflection. Then we also studied something for law of refraction, where light rays bend if they change medium. We studied that. We also need to cover that over here in computer graphics. So a lot of things we will draw from physics and coordinate geometry and vectors and all that. They're needed for fundamental concepts. So this is the surface over here, a reflective surface. So light ray falls off. Here we got a light source, we got our eye, and here on this point we have a reflection. So we need to know, let me put a label to that. We need to know the surface normal vector so that we can create this angle I. Is this thing clear? Okay. The surface normal will always stand perpendicular on the surface. So if I take this tissue paper box over here and I place this remote control like this, this is going to be the perpendicular. If it's about this face, that's the surface normal. For this face, this is the surface normal. And if it's kept slanted like this, the surface normal will also be slanted, but it's always going to be standing perpendicular on the surface. So knowing that, we need to calculate the surface normal. Why do we need to do that? Because we only see an object when light ray falls on that object and bounces off, comes to our eyes. Otherwise, we don't see that. We have learned that in physics, right? Light has to bounce off on some surface and come back to us. We're coming close to the end. Let me get a paper so that I get attendance. আমি 7টায় আসতেছি, ক্লাসটা শেষ করে 7টায় আসতেছি, 10 মিনিট বাকি আমার। একটা ওজি একটু পাঠিয়ে দিন। হ্যাঁ। Okay, sorry about that. Okay, so what I was saying is that, let's say I want to see this point P. The only way I could see that is if a light ray falls on that point P and comes back to my eye. And for that, I need to know the surface normal, because otherwise I won't be able to calculate the reflection angle. Okay, because I want to know what's the incidence angle. All right. Now, when we are describing a polygon, because at the end of the day everything is a polygon, what's going to happen? Let's say we have a quadrilateral like this. And on this surface, we're talking about the surface normal over here. Then when we when we talk about this point again, we will do something very similar. We'll consider this to be a surface. We will calculate the surface normal, and then we will calculate the incidence angle and the reflection angle again. But the important thing to understand is that for each of these polygons, we need to calculate the surface normal. Actually, we need to calculate the surface normal for individual corner points. So for each of these corner points, we need to know the surface normal. So that's the question. How do we calculate the surface normal given the vertices and the faces? Any clue? What is a surface normal? What type of number is it? Is it a scalar or is it a vector? It is a vector, and I've noted that already with a arrow mark over here. What's a vector to start with? A vector is something that has two very important things. It has a magnitude or a length, and it has a direction. So the sense of direction is very much important, because whenever I'm talking about a surface normal, it gives me a direction that the surface normal is going this way or this way. So the sense of direction is very much important. Another important thing you need to understand about vectors is that they do not have any origin. Okay, so if I consider this remote control as a vector going this way, it's the same vector if I put it over here, or if I put it over here, or if I bring it over here. It's the same thing. So long as I don't change the direction and the magnitude, it is the same vector. So a vector doesn't have an origin. It only has a magnitude and a direction. So given the corner points, 3 different corner points. We don't need 4, right? Because that's what Ibrahim told us, that the minimum number of vertices we need on a face is 3, not 4. So we can do it with 3. But let's say we are given 4. It doesn't really matter. How can we find the surface normal of any surface? For example, this piece of paper, we got 4 different corner points. Okay. And how can I find out that if I keep this paper in this way, that the surface normal is going to point this way? All we are given is nothing but the corner points, the vertices of the corner points. Any clue? No. Have we heard about the cross product? Yeah, what does our cross product give us? Let us set this up. That's how you calculate the cross product. I'll come back to that AB sine theta thing. Yeah, it wouldn't matter. Let's say we're given this weird shape of quadrilateral. Actually, I can make it simpler. Let us just talk about 3 vertices like this. Let's say we're given vector A and vector B. Okay, and I want to do A cross B. All right, what would I get? Okay, so you're saying that A cross B is equal to AB sine theta. Okay, first of all, we can't even do this, right? AB sine theta, we can't even calculate this. What you probably meant is this thing. The magnitude of A times the magnitude of B times sine theta, where theta is this thing, the angle between A and B vectors. Okay, so this is a scalar value. The length of a vector or the magnitude of a vector is a scalar value. B is also a scalar value. Sine theta is again not a vector. That's also a scalar value. You multiply 3 scalar values together to get what? Another scalar value, whatever scalar value it is. So if you write it in that format, that's not right. Okay. This is not the result of A cross B. This is actually the magnitude of A cross B. Okay. But A cross B gives you a vector. It doesn't give you a scalar. There's more to that. Okay. It doesn't give you the sense of direction which you need. That's why this won't work. AB sine theta is not going to work because it only gives you the magnitude of it. That's why we really need to understand the physical significance of each of these things that we have studied before. Whenever we are talking about the vector cross product, we need to understand what does it actually give you. So I formed a parallelogram with those 2 vectors. We have vector A, we have another parallel line to vector A. We have vector V, B, and this line is parallel to vector B. So if you enclose the area, we get a parallelogram. In Bangla, we call that Samantari, right? So when you do a cross product, what you get as AB sine theta is nothing but the area of that parallelogram. So the magnitude of the cross product is the area of the parallelogram that these two vectors will encompass, and the direction, if you need to get the direction, because the result of cross product is a vector, it has a direction, will be the surface normal standing on the surface defined by vector A and B. Okay. So if I'm going to take this podium as an example, and I say that this is vector A and this one is vector B, then we have a flat surface over here. We have a parallelogram, right? A cross B will give me the area of this parallelogram, and also as a surface normal, I'll give the direction over here. It's going to stand perpendicular on this surface. And the important thing you should know is that when you calculate the surface normal, you have to use the right-hand rule that you learned in physics. The way this is defined is that if you do A cross B, it's not going to be the same as B cross A. When you do A cross B, you have to place your palm like this on A, and then you curl your fingers towards B, and your thumb will point towards the actual direction of the cross product. And that's why it's named right-hand rule, because I'm going to use my right hand, not my left hand. Okay? So again, taking this tissue paper box, if we have vector A going this way, vector B going this way, A cross B goes like this. If I do B cross A, my thumb points downwards. That's why A cross B and B cross A, they're not the same. They can't be the same. So if you go counterclockwise or if you go clockwise, has totally two different meanings. Okay. So what we brought it down to is that we are given a polygon, right? We're given a polygon with three vertices, and somehow if you can form two vectors, one vector over here, another vector over here, you can easily calculate the surface normal by doing the cross product. But we have a problem now. We are given coordinates, we are not given vectors. Okay? And that's where I want to stop. In our next class, we'll continue with this thing. We'll learn how you can convert these coordinates or these points to vectors, because once you have the vectors, you can do a cross product on them to find out the surface normal. Okay? And if you forgot how to do the cross product, we'll look into that. But I'll say that try to study that home. We use the determinant format to calculate the cross products. Okay. Any question on any of these things? Nothing? All right. Okay, so I'll stop recording over here and post it on our group. Did you all join the course group?